So in this video we're going to be looking at functions, but we're also going to start the grade 12 curriculum. But the functions, what we're going to do in this unit, I just want to do a quick review of functions before we start expanding our knowledge on it. So we remember from functions some of the key things that we need to remember. So the notation, first of all, f of x is equal to whatever the function is, like x plus 1. You have to also remember when we do have any sort of, like, say, function, we need to remember that every input only has one output. So for every x value, we should have one output y value. So another way of looking at that statement is the vertical line test to see if something is a function. At every time you draw a line down the vertical axis, you should have only one. Doesn't matter where you put this line, it should only go through it one time. What else can we look over? This is an example of a function, but you can also have an example where it is not a function. So something like this would not be a function, because you do the test, you have two spots here that would be defined as a function. Let's remember what absolute values are. If you remember, we had, say, the absolute value of -3 is equal to 3, and the absolute value of 3 is also equal to 3. So let's remember, we have to keep that in mind and remember the function for say y equals the absolute value of x. That is going to be, so y equals x is this, but the absolute value will not be negative, it will also be positive. That is our absolute function. We have to remember that. I don't know if we covered these things, but there are some definitions that we can go over. So something called the interval of increase. The interval of increase is basically the interval or intervals, it could be plural, of a function's domain where the y values are getting larger, so moving from left to right. And then we also have, let's just put decrease as well, and that's the exact opposite. I think we did do this. No, we didn't do it. So we can learn also about odd functions. Just brush up on odd functions. An odd function, you have to look at the degree of a function. So y equals x squared is an even function, because let's just put even / odd. This is even because 2 is an even number, and what happens is that y equals x squared will do this. It'll come from up and finish it up, or if you do negative, it'll be like this. It'll come from down and end it down. So it's an even function. An odd function will do something like this. It won't go in the same direction that it came from. So it came from the bottom but ended at top, or you can have something like, like that. An odd function can do like 1, 2, 3, 4, 5, 6, and like that. So those are things you can look at. Another two things that we should keep in mind are something called a continuous function, and that is basically a function that has no breaks in it, has absolutely no well, this is gonna lead into the next a discontinuity could be like, a discontinuity is a break in the graph. So that point at which it breaks, that's where it's a discontinuity. For example, when a graph will do something like this, if it has this the y-axis as an asymptote, that'll be a discontinuity because it has points for every x value except 0 for x equals 0. So we do remember our domain and range. Domain is where we can define all of our x values, and range is where we can define all of our y values. So a lot of fun things to go over. If you need a refresher on how to map out graphs, there's tons of videos that I've already done graphing different types of, or sketching graphs of different types of functions. You can just go back there and see what you want to relearn. What else can we do? We can go over inverse functions quickly. In which, if you remember, if you look at it on a graph, like if you had, say, a function like this, if you drew out an imaginary line like that as y equals x, you would just flip it upon that. So whatever this is, you just flip it like that, in which this would become like that. But if you wanted to do it algebraically, you just swap out the x and y and isolate for y again. So for example, if you took the volume of a sphere, which is volume equals 4 over 3 pi r cubed, if you wanted to find the inverse of this, you would just isolate r. Right now, v is a function of r. So if we swap it out to make it the opposite, we can do multiply this by 3, 3v equals terms of functions, it's basically just a review before we get into the actual, when we go into the next chapter, where we start learning about, or we start interpreting functions as rates of change, where we have things such as meters per second, or meters per second, which is meters per second squared. This would be speed, this would be acceleration, all things that are used very heavily in the real world. So stay tuned for that. And yeah, I think I'll just stop this one here, and I shall see you in the next one. Okay, so in this video we're going to be looking at the rate of change. So the average rate of change, by definition, is, well, like in relation to the change of a quantity given by a dependent variable. So for us, let's say it's y. So the delta in y over a corresponding change represented by another independent variable. So let's say x. So for us, mainly what we're going to do, in many cases, will be a change over time. But we can keep an open mind. So if f of x, if y is equal to f of x, then, and say x1 is smaller than x2, then we can say our rate of change, our delta y over our delta x, is f of x2 minus f of x1, which are y values, over x2 minus x1. And this is going to make more sense in a bit when we look at an example. I'll just leave that there. So let's look at an example with, say, bacteria. Say we have time. So our time in hours. Let's say we have 0, 2, 4, 6, 8, 10, and then we have 850, 1122, 14, 81, 1954, 2577, 3400. See, we're looking at this chart. And say we have bacteria here. Now we see at 0 hours we start off with 850, and then we have 1122, and then we have 1481, then 1954, 2577, and 3400. So say we want to look at the rate of change. And we want to see the difference in the rates of changes between each one of these intervals. So let's look at 0 to 2 hours first. So let's do the rate of change between those. How much bacteria did we have grow in the first 2 hours? So the difference in the bacteria is going to be 1122 minus 850. just write that here. So 136. Let's put delta just to see the rate of change. Now we can do the rest for the others. So say we have oh wait, that's gonna get confusing. Let's do for these two. And then for these two, and for these two, and these two, and these two. So we found this one to be 136 difference. Now you see the time is growing at a steady rate by 2. So all I need to do is take the difference between this value and that value and divide it by 2. So this one will give me 179.5. 1954 minus 1481 should give me 473 over 2, 236.5. This one, 2577. Subtracting 1954, that should give me 623, and then divide that by 2. I should get, what is it, 311.2. 0.5. 311.5, and then we have 25. No, sorry. Well, 3400 minus 2577. When you subtract those two, you should have 823. You divide that by 2. You should get 411.5. And you can see the rate of change is growing. So not only is the bacteria growing over time, the rate at which it's growing is growing as well. So if you were to draw that out, here, and you had say this is 0, then you had well, let's draw these out. So 1,000, 2,000, 3,000. You start here, and then you do intervals of 0, 2, 4, 6, 8, 10. It would go somewhat from here. That's 10. Let's do 2, 4, 6, 8. 6 is somewhere in 1900s. 8 is 25 something. It'd go So my point is, it's not it's a straight line. It's actually a slight curve. And that is the rate of change, which is changing. And you can actually find the rate of change at any given point by finding a secant line. So what is a secant line? So say you have this curve. And you want to find out the rate of change here. All you have to do is plant a line that goes through that point. Or if you want to find the rate of change between, no, this is a tangent line that I almost confused a lot of people there. So let's take one more example. So let's do an example of, say, the real world where you have say you're doing a car rental, and the car rental charges you $35 per day, plus an additional 15 cents per kilometer that you drive each day. So we can say that we're smart enough to write a function for this. So the cost of the distance, or the daily car, or the days, the cost of each days is going to be 0.15 times d being distance in kilometers, plus 35 on any given day. So now we can look at the average rate of change here. So if you were to draw this out or sketch this, we could say that this is the distance. Say you start off at 0 and you can do 50, 100, 200, 300, so on. Oh, that's not even, should be 150 and 200. Then you do the cost, 10, 20, 30, 40, 50, 60, 70, 80, and so on. So we know that if we were to draw this out, we start at 35, and then we do 15 cents per kilometer. So the more she drives, it just keeps going. So we can tell this, or we can see right away that the rate of change is constant in this one, in this example. Because our line is straight. And if you were to pick any 2 points here, say 0 to 100, let's say at 100 she's at 50. Let's just say that's true. And then you would plug it into the formula delta C over delta D. Delta being the change in the cost. Oh, this is the cost here. The cost, the charge at 100. So C at 100 minus C to 0. So say that 100 would be 50 minus 35 divided by 100. So then you'd have 50 minus 35, which is 15 divided by 100, which is 0.15. And that's exactly what she's getting charged anyways per kilometer. So we can confirm that the rate of change for her rental is only dependent on this, on her kilometers driven. So yes, that is us using math to state the obvious. So yeah, rate of change, heavily used in physics and chemistry. So stay tuned in the foreseeable future when we cover physics. It's going to be fun to learn about all the different types of deltas and rates of change. So yeah, that is all for this video on rates of change, and I shall see you in the next one. Okay, so let's solve problems involving rates of change. So let's go with an example. Say we have a Ferris wheel. Let's pretend that looks like a Ferris wheel. And say that we have the elevation from the ground to any given point at where a certain person is. So let's say I am on this Ferris wheel and I'm here. And we're going to say that h of t is going to represent the height above ground in meters, where I am, and t is going to be time, and the function that's going to represent my height is going to be 5 cos 4 t minus 10 degrees plus 6. It's going to be a cos wave because I am going up and down. So we want to see at what time, at what exact time. Say we're going to take an educated guess and say at 55 seconds I will be closest to the ground at here, and we're going to try to prove that or check it or see if that's true. So what we're going to do is, instead of 55, we're going to look at 54 to 55, because basically when we look at the rate of change at these two, if we have a rate of change that is going very at a decline like this or an incline like that, you're going to have a proper number, like a number that's going to be really positive or really negative. But at the very bottom, you're going to have a line that is a rate of change that is very close to it's going to be like this. That line, the tangent line, is going to be 0. Or, yeah, 0. So, let's look at the delta here. So we have h at 55 minus h at 54 over 55 minus 54. So if we plug in 55 into this in a calculator, we should get 1 meters per second. Because remember, our numerator is in meters, because h of t is the height in meters, and t is in seconds, so we are doing meters per second. And now we're going to do the exact same thing with h at 56 minus h at 54. And that is going all divided by 56 minus 55. So let's just put a line here. That's going to be 1.0122 minus 1 over 1, which again is going to give us 0.0122. So, what do we know now? That based on this information, at 56, you're going to have 1.0122 meters above the ground. So, if you had like a like the bottom of the Ferris wheel, this is 1 meter above ground at 55 seconds. At 56, it'll go back up slightly more. So this is going to be 1 meter, and then this is going to be, at 56, it'll be 1.0122, and then at 54, it'll be right here, the same as 56. It'll be 1.0122, and there you go. So, basically, the rate of change that we've seen from here to here is negative, and the rate of change from here to here is positive. But if we did a rate of change from here to here, you'd have 0. So it's not unwise to say that the lowest point will happen between 54 and 56. So 55 would make a great estimate and therefore would become the lowest point. So let's look at one more example with the rate of change. So let's say we have f of x equal to x squared plus 4x minus 21. And we want to see that, or prove that at x equals negative 2, that's where the minimum point happens. So we know that this is a parabola formula with a positive in the front, so it's going to be like this somehow, somewhere. I don't know exactly where, but it's going to be opening upwards. So let's find or prove that x equals -2 at some point. So the way we're going to do this, we're going to estimate the slope of the tangent to the curve at when a is equal to -2 by writing the equation or an equation for the slope of any secant line of the graph f of x. So we're going to write the slope is equal to the function of -2 plus h minus f of -2. So we're going to basically say that h is going to represent a small amount of difference from the -2, and we're going to find the delta from there, the difference in that height. Remember, this is a generic way of finding a slope. This just means that a point at -2 that is just slightly off by a little bit, we're going to use that point and the difference from there to find a slope of a tangent line. So to find or to estimate the slope of the tangent line at x equals -2, well, this is why it's going to be somewhere here. Let me just correct that. Let's put this somewhere. I don't even know, there. At x equals -2, we're going to use 2 points and the difference quotient. So for 1 point, we're going to use this. Well, actually, we're going to use -2 comma -25. So let's put that there. So with that point, and then we're also going to use another point which is going to be generic. So that point that we're going to be going towards is going to be -2 plus h, the x coordinate, and then the y coordinate is going to be the f of that. I hope it's not super confusing. But once we plug it into our slope formula, it'll make sense. So when you plug these two numbers in, you're going to have something like this. Let me put that somewhere else. And now when we simplify this, well, this is all still over h. So when we simplify this, we're going to get we should get 4 minus 4h plus h squared minus 8 plus 4h plus 4 all over h. So the plus 4 plus 4 and minus 8 will cancel out. Negative 4h plus 4h will cancel out, leaving us with h squared over h, which is just h. So, if we were to use a very, 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 very small value here, so all we've done so far is prove that we can use h as a small increment here. So, we know that the slope at where all we've done so far is prove why we can use a variable h to use an ambiguity to say that the tangent line is going to be close to 0. The slope will be 0, so we can say that h is going to be so small. It'll actually become the slope at which we're changing it at, and also so when we look at these two differences, one here and one here, when we do the delta of the two, so say we do the delta of these two rates, so we can have 0.01 plus negative 0.01 over 2, and we're going to have, basically this is going to cancel out and give us 0. By that logic, using 0.01, we can prove this, that at f at negative 2, you have negative 25, correct? But if I add 0.01, I'll get, well, that's not 0.01, that's 0.1. I should get negative 24.99 if I plug it into this formula. And if I go over f at negative 2.1, I'll also get negative 24.99. And there you have the difference, that h value that we were looking for. So this one and that one, they're off by 0.01. Which was our h value that we used. So, we can say that because the tangent line that we introduced, since that is equal to 0 when x is equal to negative 2, and also since the values just around f at negative 2 are greater than the value at x equals negative 2, our minimum occurs right here at x equals x equals negative 2. So I hope I confused you as much as I confused myself. But yeah, that's all for the video on solving some problems that have rates of change in them. And I shall see you in the next one. Okay, so in this video we're going to be looking at polynomials. So let's start with this f of x is equal to negative 3x to the power of 5 plus 4x cubed minus 8x squared plus 7x minus 5. Say that is my function of x, and basically what I want to do is just look at this, and just by looking at this I want to come up with a rough sketch of what this function might look like. So there are a couple of things to note here. One thing that we're going to do just to find the behavior of this is to see the behavior of the function when we send the x value towards infinity. And well, first we'll start with negative infinity, and then we'll go on to the positive infinity. So in the x value is going into the negative side. If I was to plug in a very big negative number into this, the biggest factor influencing the output here is this right here, this first term. Since this first term is to the power of 5, it's going to have the most significant impact on the behavior of this polynomial. So if I put a gigantic negative number, it's going to be a positive number here. So I can say that as x, the value of this function, whatever's going into this way, into the negative area, I know that I'm going to get a y going to upwards of a positive number, so this is y. Y will go to positive infinity. And similarly, if I do the same for a positive value, I'm going to get a negative value. So as x goes all the way to the positive infinity, a big number will only get me a negative output based on this first term here. So I'll get a negative infinity for y's behavior. So far I have the behavior of the positive and negative values of the function. Next we're going to look at the zeros of the function. So, based on what we have so far, with the value going like that and ending like that, this could be looking like that, something like that, or it could even look like, something like that. So that's what we know so far. But then again, we can also look at other factors here. Let's just draw this out again. So when we look at the zeros of this, so if we were to factor this completely, we have 1, 2, 3, 4 of these. So yeah, based on what, just by looking at this, we could say that this f of x function can have 0. Let me just 0, 2, or 4 turning points. So it could not turn at all, or it could turn let's look at the degree of the polynomial being 5. So that's the highest degree right there. The degree of the function is 5 because of its highest term exponent. So, because this is 5, we can say f of x will have at least 1, 0, but also max 5 zeros. So these are characteristics. So this right here, and this part, and this part. These are characteristics we can take away just by looking at the polynomial, that it could actually have 1, 0, so we can do this. 1, 0, or it can do 2 zeros. Sorry. Yeah, it can like do 1. Like that, 2 zeros, or even 1, 2, 3 zeros. You get the point. But basically, I'm saying it can have zeros. So that is a few things. It's going, or some characteristics to look at when trying to understand the behavior of a polynomial. And behavior, this is what we did here. And behavior, to see what happens when x goes to negative infinity and the positive infinity. And then we also want to look at the leading coefficient of this, the negative that we have here. That plays an impact on the behavior there. And then we also want to know that if this degree here, is it positive or negative? Because a negative, sorry, what am I saying? Even or odd. Even means it will do whatever it does, but then end up in the same direction it came from. Odd will do, so it can do that, or it can go like that. But odd, in our case we have odd, it will always start on one side and then end the other side. Same like for me. So if that was a positive coefficient, it would have done this. But since we have negative, it's doing this. And then like we looked at the number of turning points. So if the degree is n, it will have n minus 1 turning points. So our case is 5, so it'll have 4 turning points. What else? Number of zeros. It will have if n is degree, n minus 1 turning points up to n zeros. We can have up to n zeros. So these are the main takeaways from I guess this that example. I just wanted to introduce that example. Let's try doing this let's continue on polynomials. I don't want to finish up so quickly there. So let's say we want to have a cubic function. So we want these zeros, and we want to write a cubic function, and we want the y-intercept to be 6. So let's write this out now. So let's get our function f of x equals a x plus 2, because I have a negative 2. And we have x minus 3 for R3, because x minus 3 equals 0, x equals 3. That's what we want, that's why I'm writing negative. And then we have, if you were to do x equals 2 over 5, 5 times x equals 2. 5x minus 2 equals 0. So I can put that in here. 5x minus 2. Can't say I didn't explain. So that is our formula, and we want to find our a value. And lucky for us, we have a y-intercept, which is a point. So that will give us x comma y 0 comma 6. So our f of x value of 6 is going to be a, and then our 0 plus 2, 0 minus 3, 5 times 0 minus 2. So we have a times 2 times negative 3, 5 times 0, 0, so negative 2. So we have 6 equals 12a, and that leaves us with a equals 1 over 2. So now we know what a is, we can just put that back here. And see how easy that was. We found a cubic function with the 3 zeros and its y-intercept. So, very straightforward stuff. Well, that's all for this video, and I shall see you in the next one. Okay, so in this video we're going to be looking at dividing polynomials. There's no easy way to do this, so let's just get right into it. Let's say we have a polynomial that is 3x cubed minus 5x squared minus 7x minus 1. Right? And let's say I want to divide this. I want to divide this by x minus 3. So what I'm going to do is the old-fashioned way with the division. Let me give myself some space there. So we have x minus 3 that we want to take out. So let's go over this step by step. So what I'm going to do first is look at just this first term, x, and this first term here. Can I divide 3x cubed out of x? And the answer is yes, because 3x squared would be what would be left after that. So I'm going to put 3x squared up here. Now that I have this 3x squared, I'm going to take this 3x squared and multiply it by this entire x minus 3. So if we write that out, 3x squared times x minus 3, I end up with 3x 4x cubed minus, into that, 9x squared. So, what are we going to do now? We're going to take this right here and put it here. 3x cubed minus 9x squared. And we're going to subtract this. So these will cancel, and I'll be left with a 4x squared. And what happens after that? These come down, and I'm left with negative 7x minus 1. So what I'm going to do after that is the exact same thing I did the first time. I'll take this x and this 4, which will be 4x times x. So this 4x is what I can divide that by. So I'll have plus 4x. And now when I multiply that 4x times x minus 3, I get 4x squared minus 12x. So I'm going to write that here. 4x squared minus 12x. I'm going to subtract that. These will cancel, and I'm left with 5x. And then guess what? This will come down again. This will come down, and then we'll try it again, and I'll get a 5. I can factor a 5 into this first term here. So 5x minus 15 is what I'll get. And then subtract that. These will cancel, and you're left with 14. So 14 is actually going to be your remainder. So now that you have completed the whole thing, if we were to write out the whole thing, 3x cubed minus 5x squared minus 7x minus 1, this is the exact same thing as writing, once we've divided x minus 3, we've taken that out, we're left with this up here. 3x squared plus 4x plus 5. But we have this plus 14. So that is our divided product. And we can actually expand this and simplify it, and we'll actually end up with this again. That is the miracle of long division. So let's try another one. Let's do let's do let's do sorry, let's just get this right. X to the power of 4 minus 2x cubed plus I want to say this is this is what we're going to tackle this time. You might be confused as to why there's this here. Well, this problem is actually this x4 minus 2x cubed plus 5x plus 3 divided by x squared plus 2x plus 1. There is no x squared in this numerator here. The reason why we put it there though is for formatting. This actually means nothing. It's 0 times that. There's nothing there. So that is how, or like one thing to notice before you start putting these out and start doing this. Another thing, these should be in order of highest degree to lowest. So if you ever see a problem where it's 5x plus x to the power of 4, put the 4 first, go from highest to lowest always. So let's start. Let's put x squared into x4. I know we can get x squared out of that. So then we have x4 times that entire thing. x4 times, x squared times this, the divisor. So we'll have x4 times 2x, which will give us plus 2x cubed plus 1x squared. Because 1, just putting the 1 there. Let's subtract that. That will cancel. That will give me a double negative because I'm subtracting. So I should get negative 4x cubed. 0 minus 1 is negative 1x squared. And I'll bring down the next one. Now let's do it again. Let's take the x squared into the 4x cubed. And I know I can take out a negative 4x. So let's multiply this negative 4x here. So we should get a 4x times x squared should give me negative 4x cubed. And then I should have a negative 8x squared minus 4x. So I subtract that. And then I'll get 7x squared plus 9x. Bring down the 3. Let's do this again. X squared into that, I'll get a 7. So then I'll multiply the 7 there. So 7x squared plus 14x plus 7. And I'll be left with negative 5x minus 4. So what does that leave me with? The remainder being that. So if we were to rewrite this entire thing, if we rewrote it, it would be, let me just fix this up here. We would have the x squared plus 2x plus 1, x squared minus 4x plus 7 minus 5x minus 4. That is what you would be left with after dividing this polynomial by this polynomial. You'd have this polynomial factored out. This is what would be there, and this is the remainder. So that is all for me to show you in this video. I can leave you guys with the problem here. this polynomial 13x minus 2x cubed plus x4 minus 6. Find out if x plus 2 is a factor of this. That is my homework for you. Go crazy. X plus 2, sorry. So yeah, leave it in the comments and have fun. That's all for this video. I shall see you in the next one. Okay, so in this video we're going to be tackling factoring polynomials. So, let's look at something called the remainder theorem. The remainder theorem. So, let's say we have a polynomial f of x. Whatever this polynomial is, when we divide this polynomial by, say, another polynomial that is x minus a, then we can say that the remainder of that division is equal to f at a. So, what can we do with this piece of information? Well, for starters, we can say that if the remainder, say we do this whole division here, say I have the x minus a, and then I have the whole polynomial here, and then I end up with some remainder, right? Like I have some polynomial, but then at the end I have the remainder, right? So, what I'm basically the theorem states that if I was to plug this a into this function here, I would actually get this. However, if you plug if you decide to do the division and get a remainder of 0, then you can say that x minus a is a factor of f of x. If you plug that in and get 0. So, this is kind of a shortcut when we start looking at things. So let's try using this theorem to our advantage in an example. Say we have x cubed plus 7x squared minus 2x minus 5, and I want to divide this by x plus 7. So, remember, let's say our total like that. So that's f of x. Let's say f of x, say we already factored it, plus 7. And we're left with the quotient plus remainder. Now remember, x minus a. So in this case, a is equal to -7 because we're subtracting it. So it's going to be x plus 7 is going to give us a is equal to -7. So by that definition of our remainder theorem, f at -7 is equal to 0 times the quotient plus remainder. And when I put this -7 here, then you'll actually see this entire expression come to 0. Once you punch this into, that's because when you plug -7 into here, you get this 0 here, and then you have this quotient, which is just that. So this entire thing is just going to be f at -7 is equal to the remainder. And that's why we say that f at a is equal to the remainder when you have this. So if you were to actually plug in this number, so let's put that in there. That was just explaining the proof. But if we were to actually plug in f at -7 is equal to -7 cubed plus 7 times -7 squared minus 2 times -7 minus 5. 7 times 7, 49. Well, if you do this in a calculator, you should get -19. So you can just say, based off of the remainder theorem, that we have a final quotient. The remainder is going to be -19. And you can actually do that out if you want to prove it. Just divide these two, divide this polynomial by this polynomial. You'll find the quotient to be -19. Let's look at another one. Let's go with y equals 4x 4 plus 6x3 minus 6x squared minus 4x. So what I want to do here is find the zeros. And we're going to do this or achieve this by factoring. So I see that I can factor a 2x right out the gate. And we've done tons of videos on factoring in the past, so you can check those out. So if we would take out the 2x we have, I'm going to rearrange this in a way. Actually, no. I'll do that later, step by step. Let's say take out the 2x from the 4x plus 3x squared minus 3x minus 2. So now I'm left with let's see, I can easily factor out, or if I was to rearrange this, let's see, how could I do this? Let's let us factor out let's do the division. Let's x squared minus 2. Could that work? Now let's try grouping 2x cubed minus 2 plus 3x cubed minus 3. Nope, that would also leave us with something. Let's try finding a factor. Let's try, say if this is f of x is equal to that, f at 1 is going to be 2 times 1 cubed plus 3 minus 3 minus 2. So those cancel. F at 1 is equal to 0, which means, okay, according to our theorem, if x minus a is a factor, it's a factor of this, if, as long as f at a is equal to 0. So that's my shortcut that not my shortcut, our shortcut in math. So we can say that x minus 1 is a factor, so I can factor out x minus 1, and we can do the long division. So, for the sake of simplicity, I'll just write this here. Let me just do this, x minus 1. I have a 2, 3, negative 3, negative 2. 6x cubed minus 2x squared minus 12x. X to the power of 4 minus 6x to the power of 3 minus 2x to the power of 2 minus 12. X to the power of 3. So yeah, happy mathing to you. Enjoy that, and I shall see you in the next one. Okay, so in this video we're going to be factoring cubes. So, cubes being, a sum or difference of cubes, being a plus b, both of them cubed, or a cubed minus b cubed. So, we're going to introduce the rule, which is let's do the sum first. A plus b. Well, a cubed plus b cubed is equal to a plus b times a squared minus ab plus b squared. And there you go. So let's tackle an example. 27x cubed plus 125. Let's just rewrite that here. We can look at these two terms individually and say that they are cubes of other values. We know 27 is 3 cubed, x cubed is x cubed, and that's just the powers come together, power of power. So we have 3 already here, 3x cubed, and 125 is the same as writing 5 cubed, because 5 times 5 is 25, times 5 is 125. So, according to our new law here, if a is equal to 3x, b is equal to 5, so this 27x cubed plus 125, that is going to be equal to 3x plus 5 times a squared, which is 3x times 3x, which is 9x squared, minus a times b. So multiply these two. 15x times b squared. Plus b squared, which is 5 times 5 is 25. And there you go. Simple as that. So we can do this again in a different, let's just, while we're here, we'll just switch this to, let's swap that with that, and that with that, and that with that. That's all there is difference here. Now we're going to do an example with a cubed minus b cubed. So, a cubed minus b cubed, we have the rule here, a minus b times the trinomial of a squared plus a times b plus b squared. So, let's look at an example. Let's say we have 7x to the power of 4 minus 404 us why this is to the power of 4 when I thought we were doing cubes. So let's factor out an x. Oh wait, I forgot an x here. So we are going to factor out an x, but not just an x, we can also factor out a 7. So 7x, because 448 is divisible by 7. At which point we're left with x cubed minus 64. And we know that 64 is a cube because 4 times 4 is 16 times 4 is 64. So let's look at this from our perspective from before. A is equal to x, b is equal to 4. And let's write this out. What is so we still have our 7x, but let's now take this difference of cube and then put it into this formula, this identity. So we have a minus b, which is going to be x minus 4, and then we have our a squared, which is our x squared, plus our a times b, which is 4x, and then our b squared, which is 4 times 4, which is 16. And there we have it. That is our entire difference right there. So let's look at one more. Let's look at x9 minus 512. Let me just move it over. X to the power of 9 minus 512. So let's see if we can do the same thing here. Can we identify these as cubes? Well, for one, x to the power of 9 is a cube because we can do x cubed power of the power becomes 3 times 3 is 9. So that is correct. And then we have 512, which is basically 8 times 8 equals 64 times 8 equals 512. And that is that. So now we have our 2. We have x cubed, and then we also have 8 cubed. So that gives us a is equal to x cubed, b is equal to 8. So let's write this out in that formula. A minus b, which is x cubed, minus b, which is 8. We have a squared, which is x cubed squared, so this will multiply in, giving us x6 plus a times b, which is 8x cubed, plus b squared, which is 64. And there we have it. That is our difference and our sum of cubes examples. So let's see. wonder if I should give you guys something hard to do. I mean, why not? You could do try it out for yourselves. Do I want to give a cube or something more difficult? Well, we'll stick to this for now. 64x cubed plus 27y cubed. Well, there it is. Good luck. I hope you enjoyed this video, and I shall see you in the next one. Okay, so today we're going to be doing rates of change in polynomial expressions. So we did an intro video to what rate of change is. So we remember our average rate of change formula is our f at our second point minus our f at our first point divided by our second x point minus our initial x. So basically y2 minus y1 over x2 minus x1. That is a quick overview of that. We're going to, in this video, basically see how we can see rates of change in polynomial expressions. So let's say I have a polynomial expression f of x, which is equal to x minus 3 cubed minus 1. So, what we want to do here, we want to look at the average rate of change from x equals 2 to x equals, let's say 5. So, if we look at our rate of change function, it's going to be f at x2 minus f at x1 over x2 minus x1. So let's do that. Let's plug in. So our x1 is going to be 2, our x2 is going to be 5. So let's plug in our 5. F at 5 is equal to 5 minus 3 cubed minus 1, which is 2 cubed minus 1, which is 8 minus 1, which is 7. Okay, so we have 7. Let's do now our x1, which is x is equal to 2 now. 2 minus 3 to the power of 3 minus 1. So that'll give me negative 1 cubed minus 1, which is equal to negative 1 minus 1, which is equal to negative 2. So that'll give me negative 2. example, let's say I have a function. Let's say that it goes like this. Let's say that is 4. Let's say that is 2. And it goes through the origin 0. Let's say this is 4. Okay. It's a pretty rough sketch, but say we want to know that what is the instantaneous rate of change at the point 2, 0, which is right here. That's what I want to know. So, very quickly, we can actually just look at this graph and see the 3 zeros. So we can say that the formula for this is equal to a times the points, which is going to be at 0. So x, and then at 2, x minus 2, and x minus 4. And then since we know a point at which it's going to go through, we can use that. Say 2, well, if we plug in 0, all 0 is going to be one of those. So 0 will give me a 0 there. So I wonder if I can. Well, let's try using this point. I know I drew it really. Say I know that it goes through. This point 1, 3. I can plug 1, 3 into here. So I can say 3 is equal to a times 1, 1 minus 2, 1 minus 4. And that will give me one second. I'm just now realizing I missed a squared here because it is a parabolic point over here. So because it touched like that and went off, this becomes the parabolic point on the as the 0. So that means that is going to be squared at that point. Yeah, my mistake. So that should be squared as well. So continuing on here, I should have just write a formula for the slope that we're trying to get here. And if you remember from our rates of change formula, we're going to start by, let me move this. We're going to come up with the slope for our tangent line. So we have our slope is equal to f at a plus h, h being our little difference. F at a, well, our height difference, the rate at our second point. Well, and that'll give us, in our case, we're looking at the point 2. So f at 2 plus h minus f at 2 over h. So let h equal 0.001. So we're going to have our slope is equal to f at 2.001 minus f at 2 over 0.001. And now all we have to do is plug this in. So f at 2, we know right away, if we put a 2 in there, this becomes a 0. So the whole thing becomes 0. So f at 2 is actually going to be nothing. That's a 0. But this, on the other hand, if we punch that into a calculator and put that into there, so negative 2.001, 20 zeros. Again. If you punch this into a calculator, you actually get 0.000000450. So let's write that out here. The slope is still equal to 0. Over 0.001, and when you divide that you get 0.004. So since we know that the instantaneous rate of change here is, because it's a 0 and it's actually doing this right here, we know that we should get about a 0. So we can actually round this down to about absolutely nothing. So we can say that the instantaneous rate of change at 2, 0 is approximately 0. And that is how we do that. So I hope that wasn't super confusing. Let me see if anybody's interested in doing a little bit of math here. Just throw it down in the comments section, whatever you get. Take f of x is equal to 3x plus 1, and then find the average rate of change on the interval from x from 2 to 5. see you in the next one. Okay, so in this video we're going to be tackling solving rational equations. Bit of a typo there. So let's start just by going with x minus 2, x minus 3 equals 0. So we know that the denominator cannot be 0, so x cannot be 3. And if we were to solve this, when I say solving rational equations, we basically want to find out where these zeros are on a graph. So what we're going to do, because if we set this equation to 0 and we solve for x, basically we multiply both sides by x minus 3, x minus 3, 0 times that is out anyways, this will cancel, and you're left with x minus 2 equals 0, so x equals 2. And that means at 2 we have a vertical asymptote, which means, I don't know if we ever discuss asymptotes, but basically it's an imaginary line that a function, if it has an asymptote at that point, at that line, it will get infinitely close to it, but it will never touch it. It'll keep getting closer to it, but it will never touch it. So this function actually has a vertical asymptote, which goes down like that. I've actually graphed this out so I know what it looks like, but that's basically what we are looking for when we're doing these graphings. So let's look at another one. Let's say we have x plus 3 over x minus 4 equals x minus 1 over x plus 2. So we know right away our two as we cannot have negative denominators. Denominators cannot be 0 here. So x cannot be 4 or negative 2. So let's start solving for this. So what we can do is cross multiply. So we'll have x plus 2, x plus 3, x minus 1, x minus 4. And now let's expand. X squared plus 5x plus 6 equals x squared minus 5x plus 4. And now let's move. Well, we can start solving. We have x squared on both sides, that cancels out. We can move the 10x to one side, 5x and 5x. And then we have plus 6 on this side. We'll move that over to the 4 and subtract it on this side. And we should have a negative 2 here. So we have 10x equals negative 2, so x equals, divide 2 by 10, we get negative 0.2. So that is our solution there. So what else can we do? I wonder. Okay, let's try a word problem now. Let's see if we can do a word problem. Let's say we have a tank which contains say that the concentration of salt in the tank is given by a function c of t, which and t is minutes. How many minutes have gone by? The concentration is equal to 10 times t over 25 plus t. And c is equal to grams per liter. So now the question is, when does the concentration equal to 3.75 grams per liter? That's what I want to know. So it's very straightforward. If we have our target number that we're going for, which is 3.75, we can say that exactly that. And now, once we've interpreted this into our equation, now we just have to solve this very rational equation. So, first thing we're going to do is bring this up to that side, so multiply both sides by that. So I'm left with 10t equals 3.75 times 25 plus t, which will give me 10t equals that. So that'll be 10t is equal to 93.75 plus 3.75 t, and it's looking to be so I'll just take this t over to that side. 10 minus 3.75, 10t minus 3.75 t equals 90.75. So now I'm left with 6.25 t equals 290.75. Divide that and I'm left with 15 minutes exactly. So it will take 15 minutes for the concentration to reach that. And yeah, this one is pretty straightforward. We can also look at when it comes to solving rationals, we can also look at solving rational equalities. For example, I don't know if we ever touched up on inequalities, where we have x minus 2 is less than 8 over x. And now first things first, x cannot be 0, because that would be off. So I don't know if we ever touched up on inequalities, but inequalities are just these rules here that state that this has to be greater than that. So based on this inequality, you can treat this sign here like an equal sign. So what I'm going to do is bring this over to the other side. X minus 2 minus 8 over x is equal to 0. And that leaves me with what I'm going to do is divide I'm going to multiply everything here, all the items here. I don't know why I put equals, it should be like that. x over x squared, and I don't want that. And that would just divide anyways. Okay. So I'm good. And now I can put everything over x. So x squared minus 2x minus 8 over x greater than 0. And there you go. That is us solving inequalities. There are further rules that we can define for this when this is a positive or negative, like defining its behavior, but probably have to do a separate video on just that, so I'll leave it for now on this inequalities topic. Not really the most popular subject in what's it called? In terms of algebra, so I'll leave it at that, but I can also give you guys this. Solve this. By that I mean find the x, find the zeros. I'll leave that with you and enjoy that. And that's all for this video, and I shall see you in the next one. Okay, so in this video we're going to be tackling radian measures, or the measurement of radians. Really, so up until now when we look at, let's say, a circle, and say that's the center of a circle, and we have this to here. Usually when we measure from one side or one arm to the next, we measure the angle between these two and say that this is theta in terms of degrees. So let's say this is r, the radius of the circle, theta being the measurement that we're looking for, and then we say that this measurement right here, from here all the way to this line, that is equal to a. So this is where we introduce a radian. So a radian, by definition, is the size of an angle that is subtended at the center of a circle by an arc with a length that is equal to its radius. So another thing to note is the arc that we have here. This arc and the radius are both measured in the units of length. So it could be centimeters, meters, millimeters, whatever it is. But basically A has to be equal to R. And that way theta is equal to A over R. Theta is equal to 1 because they're equal to each other. So that is how we are going to be that's basically a brief intro to what a radian is. So understand that theta is equal to 1. circle is 360 degrees. Say we have a circle with 360 degrees and we have R here, and that's 360 degrees. And A is equal to the circumference of the circle, which is 2 pi R. So, by that definition, theta, which is equal to A over R, 2 pi R over R, R's cancel out, we're left with 2 pi. So theta is equal to 2 pi radians when it comes to a circle. So when it comes to the circle, based on our understanding thus far, 360 degrees, we know that based on this being true for this, and also 360 degrees is also true for a circle, we can say that 360 degrees is equal to 2 pi radians, which means that in radians, pi is equal to 180 degrees. And that is how we measure that. So, let us divide both sides. I'm not done here actually. Let's divide both sides by pi. Because this is pi radians. Pi radians is equal to 180 degrees. That's true. But continuing this logic, if you divide both sides by pi, you're left with, this cancels out, and you're left with a 1 here. So 1 radian is equal to 180 degrees divided by pi, or approximately 57.3 degrees. I can't stress enough how important this is to understand that 1 radian is equal to 180 degrees divided by pi. This is going to be very useful to you when you need to switch between, or if you want to remember this, pi radians equal 180 degrees. Just remember this, memorize it, and it'll be very useful for you when you want to convert from one to the other. So, speaking of converting, let's tackle that right now. Let me just write that here. 180 degrees. So let's try converting 20 degrees into radians. So if we have pi rads, let me just write out the whole thing so we don't get confused. Radians equal to 180 degrees. gives us what it is in reds. So let's do the same thing with, actually, let's do the exact same thing with 225 degrees. So 225 times pi over 180. You actually get 225 pi over 180. And if you simplify this, because these are both multiples of 45 degrees, so if you simplify that, that should give you 5 over 4 pi. Sorry, 5 pi over 4. My mistake. So, now that we've done that, let's go the other way. Let's go. Say we have 5 pi over 6 in radians, and I want to measure it to, I want to convert this into degrees. So, before, when I went from degrees to rad, I multiplied by pi over 180. Now when I want to go from rad to degree, I want to multiply by 180 over pi. And it's as simple as that. Actually, wait. Let me prove it first. So if we have pi radians equals 180 degrees, I'm just going to multiply it here. So I have looking at this formula right here, I'm just going to take this 5 over 6 and put it into here. Pi equals 180, 5 over 6. And that will leave me with 5. Well, if I divide the 6 here, I should get 30 degrees times 5, it's 150 degrees. Now let me do one more, just to make sure. 1.75 radians, and I'm going to take this 1.75 and I want to turn it into degrees, so I'm going to multiply by 180 over pi. So that should give me 100.3. And there you go. Yup, looks about right. So this whole radian measurements are very fun to do. It's going to be fun when it gets introduced into the trick section as well. And if you want to try it for yourself, you can. Let's say for your homework, I say convert from to radians. Say convert 200 degrees to rad, and then also convert from radians to degrees. Try doing section. And yeah, that's all I got for you for this video. And I shall see you in the next one. Okay, so in this video we're going to be tackling compound angle formulas. So these are more towards trig identities that we're going to be looking at. So let's just start defining them. So let's say we have sine A plus B. The identity that we're going to define is that if you ever have sine A plus B, that is the same as sine A cos B plus cos A sine B. Similarly, if you have cos A plus B, we're going to have cos A cos B minus sine A times sine B. And then if you have tan A plus B, we're going to have tan A plus tan B over 1 minus tan A tan B. Yep. These are the addition formulas. Let's also put in the subtraction formulas, which is going to be sine A minus B. The identity there will be sine A cos B minus cos A sine B. So opposite sign flip there. And we have cos A minus B, and that is also going to be the flip side of that one. So cos A cos B plus sine A sine B. And then we have our tan A minus B. And you guessed it, the flip signs. So you have tan A minus tan B over 1 plus tan A tan B. I don't know how schools do it these days, but back in my day, though I sound old when I say that, we had to memorize all these. They wouldn't allow us a cheat sheet. So I don't know how it is now. Maybe you're allowed a cheat sheet, maybe you're not. So let's look at some examples on how to do these. So say we want to find the exact value of cos of 15 degrees. We can rewrite cos 15 as cos 45 minus 30 degrees. that's cos 45 is 1 over root 2, cos 30 is root 3 over 2, and then sine 45 again is 1 over root 2, and then we have our sine 30 is 1 over 2. So we can simplify all this and get root 3 over 2 root 2. That's also 2 root 2, but that's 1, so that's plus 1. Oh, that's easier. And there you go. So, let's do another one. Let's do tan of negative 5 pi over 12. And that, let's rewrite that as a fraction. Say tan is equal to negative pi over 4 minus pi over 6. That'd be very kind of hard to identify, but the more you do these things, the more easier it comes to you. So remember our identity for this. Tan A minus B is equal to tan A minus tan B over 1 plus tan A tan B. So if we start plugging these in now, tan of negative pi over 4 minus tan pi over 6 over 1 plus tan negative pi over 4 tan pi over 6. So now we're left with that is should be a negative 1 minus, that'll give me a negative 1 over root 3. And I'm getting these from the special angles table, which you should have handy or know by heart, these special angles. But if you don't, you can go through my videos. There's one on special angles to quickly learn how to have them on hand. And now we just have to simplify. So we should get the numerator, we put it all. We can rewrite just that. The denominator will be so there we have it. So let's do another one. Well, those examples were expanding. Oh no. Let's try simplifying sine 2x cos x minus cos 2x sine x. So sine b. So we can see that that is our b, and this is our a. So we can rewrite this entire expression as sine of 2x minus x, which is also just sine of x. See, very simple, very straightforward. Let's do one more where we identify that. Let's do cos 7 pi over 12 cos 5 pi over 12 plus sine 7 pi over 12 times sine 5 pi over 12. So, does this look familiar? The answer should be yes. This is our cos A minus B formula, which is cos A cos B plus sine A sine B. So we have our A, our B, and our B all in the right places. So we can basically say this is equal to cos of 7 pi over 12 minus 5 pi over 12, which should give us cos of 2 pi over 12, which of course is cos of pi over 6, and cos of pi over 6 is of course as well a special angle which is equal to root 3 over 2. So that entire thing is equal to root 3 over 2, and we could easily find that with our special angles. Yes, it really is that straightforward. So, for those of you who are interested to have a little practice, try finding this out to the exact value. That is a little bit of on your own thing to do. Put it in the comments, see what you get. But yeah, until next time, that's all for this video, and I shall see you in the next one. Okay, so in this video we're going to be tackling double angle formulas. So in the last one we did compound angle formulas. This one is double angle. So instead of like in the last one where we had compound, where we had sine A plus something B, this time we're going to have a double. So sine 2 theta is going to equal 2 sine theta cos theta. These are the identities that we're going to have to more or less get used to and apply and identify and, just keep in the back of our heads. So, cos 2 theta, actually cos has 3. The first one being cos squared theta minus sine squared theta. And finally we have our tan 2 theta, which is 2 tan theta over 1 minus tan squared theta. And now you know all of our double angle formulas. So now that we have them, let's start applying them. I wonder if people will take a screenshot before I wipe it, but anyways, let's start with 2 sine pi over 8 cos pi over 8. So, how can we identify this right off the bat? We know that we have our sine 2x is equal to 2 sine x cos x. So, we know that this is an identity which we can simplify into sine 2x, x in this case being pi over 8, which is equal to sine pi over 4. And we know from our identities that sine pi over 4 is equal to 1 over root 2. Simple as that. What else do we got? We got 2 tan pi over 6 over 1 minus tan squared pi over 6. So, do we know where this one is? Well, it's the only tan one we have, so let's not keep you into more suspense. So, x being what's in the bracket there, so pi over 6. So, equals tan of pi over 3. And we all know that pi over 3 is obviously root 3 because we're so in tune with our trigonometry. So, what else can we do? Let's see. Let's do a derivation just to keep your mind sharp. Let's see. We know that, say, cos 2x is equal to 1 minus sine squared x. Well, what I'm basically doing is creating a formula for sine x over 2. Okay, so outside, so just moving it over. Let's try isolating that. So I'm gonna move this term to that side and this term to that side, so I'll have 2 sine squared x over 2 is equal to 1 minus cos x, and then I'll divide it by 2 as well. And then I have the sine squared, so I'll just take the square root. So there you have it, our sine x over 2. I basically just created a formula for it. Literally just to have a formula for it, based off of the identities that we know. So I hope that was somewhat fun to do. I wonder if you guys be interested in doing something on your own. Let me see. Let's see if I can find some questions. Let's say I do question 1. 2 sine 45 cos 45. Give me the exact value for that. Well, of course, first express it as a single ratio, then at the end, you can also do 1 minus 2 sine squared 3 pi over 8. Let's see. You can also say use a double angle formula to rewrite some of these trigonometric ratios. So sine 40 sine of 4 theta. So let me just take that out. So try using a double angle formula to rewrite the ratio. Same with maybe cos 6 theta, or even tan of 5 theta. Let's just see what happens. Let your just go crazy. And I'll end this one here. So put it in the comment section below, your answers, and let's see what happens. That's all for this video here, and I shall see you in the next one. Okay, so in this video we're going to be proving trig identities. Trigonometric identities. So based on what we've learned so far in trigonometry, we're going to apply all of that, and proofs are one of my favorite things to do because I used to struggle with it so much. So let's start with sine 2x over 1 plus cos 2x is equal to tan x. So basically I want you to prove that this equals that. So let's get started. I'm just gonna put tan x here, and I'm gonna work with this side here and basically manipulate and simplify and expand and do whatever I want to this with facts because there's three double angles formulas for identities for cos 2x, but I'm going to use this one, cos 2x minus 1, because I'm going to get rid of that 1, and then I'm left with, so these ones will cancel, I'll be just left with 2 sine x cos x divided by 2 cos squared x. And cos squared x is the same as writing cos x times cos x. So as you can see, the 2's cancel. One of the cos x cancels, and I'm left with sine x over cos x, which is the same as writing tan x, which is also equal to what I was trying to prove. So left side is equal to right side. So much fun. Let's do another one. Let's see. Let's do let's say we have sine x plus sine 2x is equal to sine 3x. I want to prove that that is not an identity. I want to prove that, so what I'm going to do is say let x equals pi over 2. So if I sub in this pi over 2 into here, sine pi over 2 plus sine 2 pi over 2, that is going to be a 1, that is going to be a 0, so 1 plus 0 is equal to 1. So my left side is equal to 1. However, my right side, sine pi over 2 times 3, that is equal to negative 1. So my right side is equal to negative 1. So left side does not equal right side, therefore it is not an identity. That is us disproving it. So we made quick work of that one. Very easy, we just plug in a simple number and check. Now let's go back to proving. Let's say we have cos pi over 2 plus x is equal to negative sine x. So let's work with this side here. We know that this right here is a compound angle. So remember our cos A plus B formula. So we're going to expand that here. And so basically we're going to have cos pi over 2 cos x minus sine pi over 2 sine x. So we know that cos at pi over 2 is 0. And we know that at is equal to 1. So this is going to be 0. So this whole thing can cancel out. And I'm left with this 1 here. This becomes a 1 because that's what the identity is, and I'm left with negative sine x, which is also equal to the right side. And that, honestly, these are moving a lot faster than I expected. I was not expecting to get this quickly into it. Okay, let's try one more, a little bit more bigger. Let's try cos x minus y and cos x plus y. Let's try to prove this is equal to 1 plus tan x tan y divided by 1 minus tan x tan y. So let's look at the right side alone. So let's try expanding this. I'm going to look at just this side. So I have 1 plus, and if we look at the tan x, we can rewrite tan x as, sine x over cos x. And then we can write this tan y as sine y over sine cos y. And then in the denominator we can do the exact same thing. 1 minus that sine x cos x sine y cos y. And then what I want to do is multiply everything so that we can have a common denominator. I want to add the 1 to this and the 1 to that. So I'm going to multiply the numerator by cos x cos y over cos x over cos y. And then once I'm able to put all these under the same denominators, then I'm able to do this because I'm multiplying both of them. So if the numerator gets multiplied by cos x times cos y, this denominator here goes away, and that becomes cos x cos y. So cos x cos y plus sine x sine y. That's the numerator. Now for the denominator, same thing. I multiply this cos x and cos y into this 1. So I'm left with cos x cos y minus, and this denominator goes away, and I'm left with sine x sine y. And now you can immediately identify that this numerator is a compound angle formula for cos. That is cos x minus y formula. And look, the denominator as well is the compound formula of x plus y. And guess what? That is our identity that we were trying to prove from the very start. This is why I like trigonometry. minus, so I took a tan 2x out, so I should have 2 sine squared x, and I know what that is. That's one of my cos double angle identities. So that is tan 2x. I'll just write that here. Cos 2x. And let's rewrite this as because we have tan is tan 2x is the same as writing sine 2x divided by cos 2x, and we still have this cos 2x here, so this will cancel with that, leaving me with sine 2x, and that is my identity proven to and through. So that is us proving some identities with everything that we've learned. Thus far, and I'll leave you with something, to practice, if you want. Something. Well, here you can do. Well, I want to know how you could type this out into the comment section. Well, you can try it. Cos x tan cubed x equals sine x tan squared x. Try proving that. I mean, if that's easy, then you can try like cos 2x plus 1 over sine 2x equals cotan of x. I mean, try both, see what happens. Enjoy life. But yeah, that's all for this video, and I shall see you in the next one. Okay, so in this video we're going to be doing the logarithmic function. So, to jump right into it, in the past we have done the exponential function y equals a to the power of x. So y equals a to the power of x. Let's say this is a 1 on the y-axis. We have an asymptote, that is this axis. So this will forever go like that, cross 1, and forever go like that. This line right here is our y equals a to the power of x. Now, the logarithmic function, let me introduce you to y equals log a of x. So, when we look at this function here, there's a couple things to note. This little a here, which is small, like it's supposed to be written like this, log a small a little lower, and then a value x. Usually when you see this log, say a number or a variable, say a variable, or let's say a number of 5, you don't see it here, but this is actually by default set to 10, unless otherwise stated, the a value. So let's note one thing down from the start: the inverse of the exponential function y equals a to the power of x, which you can also write as, let me use the other one, x is equal to a to the power of y, and the equivalent form of that would be to write y is equal to log a of x. So let's write that down somewhere. X equals a to the power of y translates to y equals log a log ax. One thing to note is that these two functions are actually inverse of them. So if we go back to our knowledge on inverse functions, remember, if we draw an imaginary line at y equals x, then we can make a reflection of the function on this axis, and that will give us our inverse function. So in this case, it will be like this. And that is our logarithmic function. So that's how it looks. Maybe we can look a little more into what it actually means. Let me write that down here somewhere. So since we know x equals a to the power of y, and y equals log a to the x, log base a of x is they're equivalent to each other, we can say that a logarithm is an exponent. The expression itself, say log ax, this means that the exponent that must be applied to base a to get this value of x. So if that didn't make sense, this will say we have log 2 of 8 is equal to 3. So we know that 2 to the power of 3 is equal to 8. So what I was saying before is that this expression is basically giving you the exponent 3, which is here. 2 to the power of 3. 3 is the exponent here. This expression gives you whatever this equates to. When you punch it into a calculator, it gives you the exponent. If you punch in this into a calculator, you'll get 3. And what that tells you is that that number 3 is what you need to as an exponent to your base, which is 2, to get x in this case is 8. Okay, so now that we have, I want to say a very straightforward introduction. I do want to also cover the function transformations for this particular function. So let's write out the full. Let's say we have a function of x. This is the full. And there you have it. So these values that you see here are not much different than when we were doing transformations to the parabolic functions, or parabola, or quadratics. So we know that A gives you a vertical stretch or compression, and you know that if it is a negative, that means that it flips on the x-axis. Let's do k next. You know that k is actually going to give you the horizontal and you know that if it is negative, then there is a reflection on the y-axis, and you already know D and C. D gives you the horizontal that's the right word, and then C gives you the vertical translation. So these are the basic transformations for this particular one. I mean, we may even be able to, let's just do one for fun. Let's do y equals -2 log base 10 x minus 4. So we know that the original function looks something like this. And that's y equals log base 10 of x. But what if we applied a factor of 2? That would actually stretch it in the vertical stretch, and then so whatever, say this would go here, this would go So you'd have, so like that would go there, that would go there, but this is still there. I'm only applying the 2, but then you have the -2, so you just flip that over, like so. Trying to get these points. So that gives us the -2, and then we also have x minus 4, which means if that's 1, that's 2, 3, 4. I'm sorry for the mess, but and that is our y equals -2 log 10 x minus 4. And you know we went x minus 4, we went over to the right side because the formula is x minus, I think it was c or d, I forget. But yeah, you're subtracting the horizontal translation, so since we have x minus 4, we're subtracting a positive 4. If this said x plus 4, then we would be interpreting it as this and moving over to the other side. And I think that pretty much wraps the whatever we can do with this function. You really only need an intro to this function. You don't need to know too much about it right now. One thing you can do in your spare time is look up or try to figure out, if you can on your own, the domain and range for this function. And if you can do that and put it in the comment section, then you win my utmost respect. But for now, I'm going to say that's all for this video, and I shall see you in the next one. Okay, so in this video we're going to be evaluating logarithms. So by that I mean we're going to look at what we learned in our last video log, where I showed you that we had y equals log a to the x is the same as saying x equals a to the y. So keeping this in mind, let's solve for this. If we have log 464 equals x, if we were to rearrange this, we know that the base, I want to solve for x here. I know that I have to take, well, by definition, the log function, this logarithm is an exponent. The exponent of what does this whole thing, which is equal to x. So 4 to x should give me 64. And that is how you rearrange the exponent into log form and back and forth. And this comes quite handy when solving for x, always for x. So it's from here it's quite straightforward. 4 to the x is equal to 4 to the 3, so x equals 3. And this is because I know 4 times 4 equals 16 times 4 is is equal to 64. No magic there. Just good old intuition. Okay. Let's do another one. Let's do log, say, base 3, 1 over 27 is equal to x. So, same formula. 3 to the power of x is equal to 1 over 27. I don't need that. And yeah. Let's see. I know 27 is equal to 3 cubed. 3 times 3 equals 9. 9 times 3 is equal to 27. I know that. So I can write if, which is the same as saying, bringing that to the numerator is just writing that, so I can say x is equal to -3. And there you have it. Sorcery at work. So, I wonder what else we can do. Let's do log 5 root 3 of 25 equals to x. This is going to be much more interesting, but not really. 5 to the power of x, or base to the power of the entire exponent, which is equal to x, will give us this value, root 3 of 25. So, 25 is actually 5 squared, and root 3 of something is actually x to the 1 over 3. So if I have root 3 of that, let me write that here. If I have root 3 of 5 squared, that's basically saying 5 to the power of 2 times 1 over 3, which is also 5 to the power of 2 over 3. And that means x is equal to 5 to the, sorry, confusing myself again, 2 over 3. And what looks scary in the beginning is now not. And we can also look at, let's touch up on the log tens. So it's important to know this, why this is so important. If you actually punch into your calculator, I don't know which kind of calculator you might have, but by default, if you push the log button and whatever number like you put in right after that, it's going to give it to you in log 10. And you can actually check that by punching that into your calculator. because if you push in log 10 and it's going to default at this, you should get 1. Because if you do that, 10 to the x is equal to 10. What to the power? Sorry, 10 to the power of what gives you 10? Only that. To the power of 1 will give you that. And same with if you decided to do not just 10. Say you decided to do 100. Then you would get what? 10 to the x is equal to 100. So what? It has to be 10 to the 2 equals 100. So x is equal to 2. So if you put this into your calculator, log 100, you should get 2. So let's continue with that. Let's see. Some other. Am I missing any special cases that we should touch upon before we move on? Let's see. Log 6 to the 1 equals to x. Let's see. So let's put that into here. Equals 1. Okay, so 6 to the power of what will give me 1? Well, obviously 6 to the power of 0 will give me 1, because anything to the power of 0 is equal to 1. Remember that. So if you ever put a 1 in there, just know you're going to get a 0, even on the calculator. Let's do another one. Let's do now this one might look confusing to you, but let's just try, instead of putting in x, let's put in a y and see what we get. 5 to the power of y is equal to 5 to the power of x, which means y is equal to x. Well, there you go. Let's do one more. All these unique cases that we can actually run into. Just so you're prepared, let's do 6 to the power of log 6x base 6 value x. And let's say we equate this to y. So, how do we do this? We just rearrange this by looking at here. We're gonna take this and go into that form. So this term will become, right now, let me rearrange this for you so you can see. Look at this one. X equals 8 to the y, but in this case we have y is equal to 6 log base 6x. But that's our y, so that's going to become here. So that'll become log 6x, which is that. sorry, this exponent now became this that's here. And now I'm going to have my log a, which is the 6 here, this big one, and then x. Sorry, in that case, that was a y here. So that x is coming from here. So for my case, y is coming from there. So now I have these two, and obviously log 6x equals log base 6y, which means x is equal to y. Again, you might think that we didn't really actually do anything to this, but more times than others, you're really just proving things. So, congratulations on proving this. I'm proud of you. And if you want some homework, here you go. Evaluate this. Log base 3, 3 to the 5. Log, the base is 3, and the value here is 3 to the power of 5. Evaluate this and put it in the comments below. And that's all for this video, and I shall see you in the next one. Okay, so in today's video we're going to be looking at the laws of logarithms. So there really is only a few that you need to know. I'm just going to quickly give them to you before we just dive into some examples. We're going to look first at the product law, which basically states that if you have a log with the base a and you have x times y, that is the same as saying log base a x plus log base a y. So this is an identity. Similarly, we also have a quotient law. So if you have a log at the base a and you have x over y, that is also the same as saying log base a x minus log base a y. And the final one is going to be our power law, which basically states if you have a log base a with x to the power of r, that is the same as saying r log a to the power of x, which basically means you brought down the r. So I would highly advise that everybody, wrap their heads around this. It's a really good thing to, keep in mind. So let's see if we can actually do some examples with these. Let's say we have log base 3, 6 plus log base 3, 4.5. And I tell you, go ahead, evaluate this, give me what it is. We know that from our product law that, log a xy is equal to that is equal to log 3. 6 times 4.5 should be 27. And we know what the answer to that is. If log 3, 27 is equal to x, then 3 to the power of x is equal to 27. And we know that x has to be 3. Because that's what gives us, so x is equal to 3. And see how easy math just became. So let's do another one. This time let's do a subtraction. And you already know I'm going to tell you that log a x minus log a y is equal to log a x over y because of our quotient rule, our quotient law, sorry. So we have to do, and let's do our dividing because we're so efficient with math. Now that we can quickly do this on the fly. Which means I have log base 2 times 16. And I know that 2 to the x should give me 16, so I guess that's 2 times 2 is 4 times 2 is 8 times 2 is 16, so x equals 4. I should have been able to do that quicker in my head. Anywho, let's do log base 5, 3 to the, base 5, cube root 3, 25. So, if you remember you can see the pattern where I'm going with this one. If you have log base a x to the r, you can write that as r log a to the power, to the value of x. You might be wondering, what's our r? Well, actually, this we can rewrite as log 5, 25 to the 1 over 3. So, let's rewrite that over here, 1 over 3, log 5, 25. Now this expression here, log 5, 25, that should give me, that alone should give me 5 to the x equals 25, so x equals 2, so 1 over 3 times 2, 2 over 3. And really, that's honestly how easy math is. I would not stress too much about it. So far, we've only done easy things. Let's actually do something a little more messed up. Let's do this. Let's say I have this log a x cubed y squared over w. represent this in terms of log ax, log ay, and log aw. So let's start doing this. I want to basically disassemble this entire thing and rewrite it in terms of 1, 2, and 3. So the first thing I'm going to do is take this exponent here, log a, and then x cubed y squared over w to the power of 1 over 2. And now that I have that, I can move that down using our product law, which is log a x cubed y squared over w. And also, now we can use our quotient rule to now split that. If you remember our quotient rule, if you have a division, you can convert this into a subtraction. And then we have this multiplication. You remember our multiplication, we can change this to and now down here, if I have space, I can bring out 1 over 2. Remember our power rule for each one of these. Well, for these two, we can do 3 log a x cubed plus 2 log a y. Oh, sorry. I don't know why I'm putting that again. And there we have that. So now I can actually bring this into here and rewrite this, multiply this, like open the bracket up. So I can write 1 over 2 for this one. This one would just be 1 because it'd be 2 over 2. So I can write like that. And our first one would become 3 over 2. And there we have our end result from this all the way to this. And we can actually even work backwards to come up with the solution. So that is all the examples I'm going to go through this one. I'll leave you with a parting gift. Maybe, let's see. Evaluate that one. Maybe even you can do, let's see. So that's 1, that's 2, that's log base 2 of 224 and minus log base 2 of 7. So that's all for this video, and I shall see you in the next one. so in this video we're going to be solving exponential equations. So let's say we have a 200 gram of something radioactive called radon, and 16 days later only 12.5 grams remained. So the question is, what is the half-life? So what is the half-life? Let's calculate that. Well, first let's start writing our half-life formula, which we know is our principal times 1/2, which represents half-life, t over h, t being the number of days, the time that has passed, and h being the half-life. So let's plug in what we have. M of t is what remains. We started with 200 grams and we're left with, I'm going to write this as 0.5 instead. And we know that 16 days has passed and h is what we're trying to find, the half-life. So let's start solving for h. So first thing I'm going to do is give myself some space here. Let me just write that up there. So if I divide both sides by 200, 12.5 over 200 should give me 0.0625. And I'm left with that. Now what we're going to do that we haven't done before is now apply the logarithm. We're going to apply the logarithm. I'm not saying it's correct. We're going to log both sides. Because right now, from a mathematical standpoint, this side is equal to this side for a fact. We know that to be true because of this formula, which we are reinforcing. Which means that if I take the log of both sides, I should get the same number as well. And like taking the log of something is always useful, because now I have this exponent up here, which I can use the power law to bring that down here to 16 over h log 0.5 equal to this side still 0.0625. And now all I have to do is isolate this, and well, I can multiply both sides by this h and this will cancel out, and I'll be left with that. Which means I can divide both sides by this log 0.0625, and I'll be left with 16 log 0.5 over log 0.0625, which if you put into the calculator you get 4. So the half-life is going to be 4. So yeah, let's move on to another example. So, what can we do here? If we remember our exponential laws, we know that when you have 2 to the power of x times 2 to the power of, say, 2, when you multiply these two, the exponents actually add. So that's how we're going to split this one here. 2 to the power of x times 2 to the power of 2 minus 2 to the power of x is equal to 24. Now I'm going to factor out 2 to the x from this side, and I'm left with 2 squared minus 1 is equal to 24. Now I can just solve for x, which being, 2 to the power of x is equal to 2 squared is 4 minus 1 is 3. I can just divide that side by 3, which should give me 8. And I know 2 to the x is equal to 2 to the 3. X is equal to 3. Easy peasy lemon squeezy. Now, to do or not to do another word problem. Yeah, let's do it. Let's say we have an investment of 2,500. Let's say you want it to grow at a rate at 4.8%, compounded annually. The question is, how long till it becomes 4,000? So let's put that into our formula. A equals principal times 1 plus interest to the power of n. We know that we want 4,000, and we start with 2,000. 4.8 is actually 0.048 to the power of n. So, let's start solving this. We have, 2,000 on one side, 4,000 the other. Divide that, 4,000 over 2,000. Should be left with this. Oh wait, my mistake. This is 2,500. So it shouldn't be 4,000. It should be 4,000 over 2,500 should be 1.6. 1.6. What am I doing? 1.6. Correct. So now let's take the log of both sides. And use the power law to bring down the n here. And now I can isolate n by dividing both sides by this log 1.048. So I'm left with log 1.6. Log 1.048. And you punch this into the calculator, you should get 10.025. And that's how many years it will take if you have 2,500 invested, compounding annually, to at 4.8% to get $4,000. Math being used in the real world. x minus 1. And let's try solving this. Try to find the exact value of this. So let's start by taking the log of both sides because I want to bring these exponents out to play. So, using the power rule, I'm going to bring this x plus 1 out here. So I should be left with log 2. And same on this side, x minus 1. I should be left with a log 3. So, let's go ahead and expand both sides. So I should have x log 2 plus log 2 equals x log 3 minus log 3. And now let's arrange the x's on one side and the non-x's on the other side. So I should have, I'll bring this 3 over to that side. So I'll have log 3 plus log 2, and I'll bring that guy over to this side, x log 3 minus x log 2. And what I'll do is divide. See, now I can actually factor out an x from this side, like so. So I'll be left with log 2. So now I have x here. I can really just do this. X is equal to what is on this side, log 3 plus log 2 divided by what was here, log 3 minus log 2. And there you go. I've successfully taken out the x out of there by bringing them out, expanding, moving them to one side, factoring it out, and isolating it. I have x by itself, and I can punch these into the calculator and get about 4.42. That may have looked complicated, but take your time with it. Practice. Always try to isolate. Try to look for ways to isolate x on its own. And yeah, the solution will come. Anyways, that was fun. I guess if you want to try one on your own. Let's see what I got. You can do go crazy. Solve for x. But for now, that is all for this video. And I shall see you in the next one. Okay, so in this video we're going to be solving logarithmic equations. So let's start with an example. Say we have log x 0.04 is equal to negative 2. So let's rewrite this in the way that we know. We know that the base to the power of this is equal to that. And so what is that going to give us? One thing to identify here is that 0.04 is actually 1 over 25. So let's start writing this in the similar way. I know that x to the negative 2 is also equal to 1 over 5 squared, which is also x to the negative 2 is also equal to 5 to the negative 2, which means x is equal to 5. See? Easy peasy. Let's try something like this. Say we have log base 7, 3x minus 5 equals log base 7, 16. One thing to note here, maybe this is probably a new law that I haven't shown you before, but if you have a log of a and say something here, m, and then you have a log with the same base and n, if this is your equation, which we're looking at similarly here, if you have log base a of something equaling log base a of another thing, we can say m is equal to n. That holds true in math. So in this case, same log base. So we can write 3x minus 5 is equal to 16. And then this is just simple algebra. I know that looks scary, but once you apply rules, then you have a cheat code. So let's do another one. Let's say we have log base 2, 30x minus log base 2, 5 equals log base 2, 12. So let's approach this with I see a subtraction that could give me my log base 2, 30x over 5, my quotient law, equals log 2, 12. So this will be log 2, 6x, because I divided it by 5, equals to log 2, 12. And remember what we said, we can easily just say 6x equals 12 because of our law. X is equal to 2. As you can see, if you can put it into this format, you can do this very quickly. So let's do it again. Let's say we have log x plus log x squared equal to That's our product law. So according to that, we can write log x times x squared equals to 12, which is log x cubed equals to 12. As you can see, I haven't written a base here, which means by default it's 10. So let's rewrite this as 10 to the power of 12 equals to x cubed. So, how are we going to solve this? I mean, we could punch it into a calculator, just cube root both sides. That should give us x is equal to, well, we don't exactly need to, because this value here, 10 to the 12, if you do the correct algebra on it, you can just do 10 to the 4, which is 10,000. So we have x is equal to 10,000. Yeah, that's correct. Okay. Let's try doing another one. One last one. Before we wrap this series up, say we have log 2x plus 3 plus log 2x minus 3 equals 4. Now, let's approach this with all of our knowledge of logarithmic expressions and equations and the laws. So I see I'm adding two logs here, so I can actually turn that into the product law. X plus 3, x minus 3 equals 4, which means I have, if I expand that, I'll have x squared. That looks like a difference of cubes, so x minus 3x plus 3x will cancel out, and I'll be left with 3 times 3 is 9. Oh, I forgot to write my base. And now that we're here, we can write we can convert this equation into an exponent form. 2 to the power of 4 is equal to that. Let me write a little more up. 2 to the 4 is equal to x squared minus 9. So now I am here. I want to solve that, but that looks like it's just simple math. 2 to the 4 is, so x squared minus 9 is equal to 2 to the 4, which is 16. X squared, so I bring the 9 over, I'm at 25, x is equal, well, when I take the square root of that, I can actually get 2. I can get x equals 5, or I can get x is equal to negative 5. So I can just write, x is equal to plus or minus 5. And that is how we do the math. Well, terms of checking. If you want to do one, I can give you one to do and see if you get it. Match it with other people if you want. Try solving this one. These are both bases of 5. And that's a 36. Yeah. Good luck. And this, post your answer in the comments section. And this concludes our grade 12 function series. And I shall see you in whatever we do next.